The second problem we want to consider for dynamic programming is a kind of a standard problem for this type of problem solving. It's called the longest common subsequence problem. So the idea here is that you have two strings. Okay, let's and I don't really need that to be capital. Those two strings will work. Let's put another enter or two between them. And what I want to do is I want to find the longest sequence of characters that appears in order in both of them. Now, they don't have to be contiguous. Okay, so, for example, I could match up this B with that B and match up, let's see, that B with that one there, and then this C with that one there, which makes it so that like this A could match up with that one there, etc. Okay? And the only requirement is that basically my lines don't cross. Okay? So the sequence of characters B, B, C, A, B, B, C, A appears in both of them in order, but there's other things inserted in between in both of these. And we want to know what the longest such sequence is for these two strings. Okay, so going back to our rules of how do we solve the problem using dynamic programming, we figure out what our optimal solution looks like. Well, it's going to wind up being a string that is of the longest possible, and we're kind of going to solve first for just the length of the string, and we're not going to worry about what that string is. So we can write this as a recurrence relationship. So if we create a new file, actually I'm going to go ahead and read in that just so that I can start off. Okay. We can make a function, I'll call it LCS, and it's going to take two strings, which means that I'm going to need to include string reference. We'll call them S1 and S2. These are const because we're not going to change them. So this would be S1 and this would be S2. And in the recursive solution, the way we're going to work this is we're going to take in two indices. I'll call them M and N. Okay. And the idea is that M and N are going to both count down. So I have a base case where if M is less than 0 or N is less than 0, that means that I've run out of characters in one of my strings, and we can simply return 0. That's our base case there. What if we haven't run out? Well, then there's two possibilities for this. If I'm looking, for example, at the A and the B, they don't match. If I was looking at A and A, they do match. And so we need to just have another if that considers those two different possibilities. So if S1 sub M is equal to S2 sub N, then I'm going to return one value, else I'm going to return something else. What should this be? So if my two characters match, it turns out, well, I found a matching character, so I count that as part of my matching character, and then I move both M and N backwards. So I call LCS on M-1, N-1. And the reason for moving them both backwards is, well, I can't use, if I only moved one of them, then I might wind up using this same A again to match that A, and I'm not allowed to do that. And it turns out this is a safe thing to do. Once again, there's this, this has the optimal substructure. If I cut off 3 characters from one of these strings, it turns out that the optimal solution that involves those three characters can be found based upon what we had as optimal solutions for the things that didn't involve those three characters. So basically I'm cutting off from the characters that matched and just considering the strings before that, and that is a valid thing to do for this problem because it has optimal substructure. What if they are, what if they're not the same? Well, so for example, the A and the B, when I first start off here. In that case, I need to consider both the situation where I move the index M backwards and the situation where I move the index N backwards. And I need to take the larger of those. So we're going to take the max of LCS of M minus 1 comma N and LCS of M comma N minus 1 and return that value. I believe max is inside of algorithm. We'll find out when I try to compile here in just a second. So I could take these two characters, or these two strings, that string, and this string, and I could see out the LCS of S1, S2, and then S1 dot length minus 1 and S2 dot length minus 1. Let's see if I typed that all in correctly. If I did, then we should be able to compile this. Apparently the answer is no. Function LCS, invalid user-defined conversion from int to const string line 13. Oh, I know why. We need to pass in S1, S2. Add the comma there, delete the D there, and then do the same thing here. S1, S2, S1, S2. I think this is going to be a great example of why C++ error messages are so unfriendly. Okay, so now we run it, and it says 10. Can we actually get 10 out of this? So I'm going to keep going with my matching that I've done here. Right now we have 4, 5. If I can get even close to 10, I will be happy with myself. 6, 7, 8. Now for this one I can get to 9. There probably is something that I could do earlier that would make it better and make it so I could get 10. We could also try, standard thing when debugging your code would be for us to try inputs where we definitely know the answers for this. For example, here's, we'll just have 5 A's in there, and then I'll have some B's and C's, and then this other one will have not B's and C's, other things. Okay, so this string is 5 A's with B's and C's. This string has a whole bunch of things that aren't B's and C's, and 1, 2, 3, 4, 5 A's in it. I expect that the only possible subsequences should be the A's, and so we get 5. You might have noticed there, though, when I ran that, there was a bit of a pause. Okay? And that's because this algorithm, like the one for the rod cutting, is exponential. If we picture this as a branching tree, this case here, when the things don't match, so the C and the T, for example, and then the B and the J. There's a whole bunch of stuff in here that isn't going to match, and that is our worst case behavior. Winds up, it calls itself twice. And so we get a full branching binary tree which has length, or which has a height equal to the string lengths. So this winds up being exponential in our string length, and that means that it's not tractable. So now that we've seen this problem, we've defined it recursively, we'll come back in the next video and we will convert this to a dynamic programming solution.